Okay. So let me give the answer quickly. I mean, it's basically a relative motion. So relative to the ground, we assume that the ground is at rest, but the sun is moving, right, relative to us. So we know that the sun moves from east to west. Okay, but from the point of view of sun, therefore, we are moving, so our velocity is basically in the opposite direction. So these two relative velocities, right? Velocity of the ground with respect to sun, and the velocity of the sun, which is velocity of the sun with respect to the ground, they are in opposite directions. Okay. I think this was one of the quiz questions in some place, but in any case, here it's actually a rotational motion. But I mean, this kind of an argument can be used in here easily. So in any case, so we know that the sun is not doing this. Basically, we are looking at the motion of the Earth from the point of view of sun or some kind of an inertial reference frame. So in that case, we are rotating and we are moving towards east. Okay. So in any case, so I said, well, just compute the acceleration of someone at the equator. Okay. So, I mean, let me write this thing down. So there's this some axis in here, right? Let me just call it like that. This is the north-south axis. So that's this is the North Pole, this is the South Pole, right? So this is the axis of rotation. We will talk about the rotation later. But basically, we are all rotating around this axis. So in Turkey, for example, what we are doing is like we are drawing some kind of a circular trajectory in here. And the center of the circle is on that axis, okay? The simplest one is a person on an equator. So in that case, the trajectory is like this. The trajectory is, or the orbit is the equator. So I'm just going to call the radius of the Earth in here, and I'm just going to call the speed in here as VE and the acceleration as E. So V is the speed at the equator. And AE is the acceleration at the equator, right? So these are the values. So, I mean, let's just quickly talk about this. So there's this figure that we need. So that's the radius of Earth. Radius of Earth. In both cases, I'm using the subscript E, but here it means the Earth. Here it means equator, right? Okay, so in any case, so that's something that I somehow remember. So it's like 6,400 kilometers. The width of Turkey is about 1,000 kilometers. So that's about like 6 times bigger, 6.5 times bigger than our width, right? You can also think of it like that. In any case, so with this figure, I'm just going to compute things. So, well, basically the speed is the circumference of the Earth around the equator divided by the period. Let me write period in here. And the period is basically 1 day. But we would like to compute this as in terms of seconds. So in any case, it's just an approximate expression. We just need to compute the approximate expression. So as a result, I won't be talking about the definitions of what a day is, and I won't be even talking about like the precise values of these quantities, like the radius of the Earth at the equator and things like that. Okay, so if you want to compute this precisely, then you can do it by just looking at these values. So I'm just going to compute these approximately. So I'll take pi to be equal to 3. The radius of the Earth is like 6.4 times 10 to the 6. 1 day is 24 hours. An hour is 60 minutes, and a minute is 60 seconds. And it is hard for me to compute this. I'm just going to compute it approximately. So I know that this is 6, that's going to give me 1/4. So that's about like 6 in here. So that's also going to give me about 1/10. Sorry. And then we have 10 to the 6. So that's 10 to the 6 divided by 60. So what I get is like 10 to the 6 divided by 24 times 100 in here. So 1/24 is like about 100 divided by 4. Right? I'm just doing some quick calculations in here. Sorry about that. I need to do it in the opposite way. So that's 4 divided by 100, all right? Then 10 to the 6 divided by 10 to the 2. And let's see, that's about 400. And the units should be meters per second because I have used meter units in here. So let's say this is meters and that's in seconds. So that's meters per second. I made lots of mistakes actually, so that the correct value is about like 500, close to 500 meters per second, which means like half a kilometer per second. Okay. So what is striking in here is that the speed of sound, for example, is around 330 meters per second. So that means somebody on the equator is actually moving much faster than the speed of sound. But nobody notices this. Okay. So even in Turkey, we are also moving much faster than the speed of sound, right? Let's say, but nobody notices this. All right. And the reason is basically the relativity principle. Galileo has actually came up with this relativity principle because of this, right? We are moving very fast, but still we don't actually experience this speed because of relativity, right? Because the air is moving with the same velocity, or the ground is moving with the same velocity. Yes, because of everything around us is moving with the same velocity. And the same thing is true for the motion of the Earth around the sun and the motion of the sun around the center of the galaxy, right? These speeds are huge. You're going to find much bigger speeds in there, but still, because of the relativity principle, there is no problem. So what's important in here is the acceleration, okay? So let's then compute the acceleration. So that's going to be v squared over r. So I think I'm going to use 500 in here, but I could have used the other one as well. Let me use 500. So it's meters per second. So that's going to be 6.4 times 10 to the 6. So let's see, we have 10 to the 4. So that's 5 squared divided by 6.4 times 10 to the minus 2. This is like 25. 25 is like 24, and that's like 20. That's 6. So that's going to give me like 4 times 10 to the minus 2 meters per second squared. Sorry about this. I just computed this, but assuming that the radius is 6,400 kilometers, and a better figure is like around 0.034 meters per second squared. Okay. So that's basically our acceleration of a person on the equator. All right, so that's the acceleration of their reference frame. So in any case, that's basically what we need to do. All right, I'm doing this calculation on the equator. So on the equator, there is this real gravity. So that's the real one. So that's about like 9.8 meters per second squared. And then there is this fictitious gravity. Fictitious gravity would be basically pointing away from the center because our acceleration is towards the center. Just keep this in mind. So that's going to be equal to 0.034, sorry, meters per second squared. Okay. So as a result, the total gravity would be like G minus the fictitious one. Just keep in mind that I'm actually adding them up, but vectorially I'm adding them up. So the components would also be added up. So it's basically the component towards the center. Let's see. So that's going to be like 9.8 minus 0.034. So that's going to be 9.77 meters per second squared. This is something which is barely noticeable. So what's important is that ratio of the fictitious gravity to the to that one, to the actual one. So that's going to be, let's say this is around, yeah, that's 9.8. So that's going to be around 0.003, which means like 0.3%. So the correction that this fictitious gravity introduces is like even less than 1%. So that means if you're doing some kind of an, I don't know, a simple calculation for your labs, for example, and if your error of your measurements of distances and velocities and things like that, if your errors are like 1%, then this thing has no effect on your measurements, right? You can safely neglect this. But if your measurements are precise, like if you are measuring distances like within 0.1 accuracy, let's say 0.1% accuracy, in that case, you may want to take this into account, right? In that case, you may want to compute the, find the value of the gravity with like 3 or 4 digits of precision. And you may also want to take this into account. Otherwise, this is something that nobody can notice. Actually, we won't notice because we won't be able to distinguish this fictitious gravity from the actual gravity, okay? That's important. Okay, so what happens in Turkey? At Turkey, right? At the location of Turkey. All right, at our location, I'm assuming that all of you are at Ankara right now. I'll try to draw it like this, but in any case, that's the equator. So that's the North Pole and that's the South Pole. Sorry, that's the South Pole. So that's the radius at the equator. In any case, we are in here, and that angle in here is called the latitude. Latitude, right? So that's almost equal to 40 degrees for Ankara. Okay. In that case, so that's the axis in here. In that case, what we are doing is basically we are following this circular path in here. Okay. Circular path in here. So the radius of our motion is like, let me call this as r, little r in here. So let's say it like this. So that's the radius of our orbit. Okay, so that's basically given as the radius of the Earth multiplied with the sine theta. So as a result, you can do all the calculations with this quantity. It turns out that, I mean, our orbit is basically more or less the same as the orbit at the equator, but the radius is just scaled by, sorry about this, this is cosine theta. The radius of our orbit is basically scaled down by this cosine theta factor, okay? So I think that cosine theta is like, this is slightly smaller than 40 degrees, 45 degrees. So yeah, that's about like 0.7, all right? I'll take the theta angle to be 45 degrees, in which case this is 1/√2, so that's something like that, okay? In any case, so we are doing the same circular motion, except that our radius is smaller by a factor of cosine theta. Then you can show that our speed is the equatorial speed multiplied with cosine theta, and our acceleration is basically the equatorial acceleration multiplied with cosine theta. Why? because the times are still the same, and all of these distances and velocities and accelerations, if you look at their units, they are like meters per second or meters per second squared. They are essentially proportional to the length dimension. So as a result, if I scale the length by cosine theta, all of these are also scaled by cosine theta. Okay, but if you don't believe me, then you can do the calculation and see that that's the case. Okay, so let me just do it like that. So in this case, for example, in our case, therefore, our speeds would be like 500 multiplied with 0.7. This is a difficult calculation. 50 multiplied with 7, so that's going to be like 350 meters per second. Still, we are moving faster than the speed of sound. What about the accelerations? Our acceleration would therefore be like 0.034 multiplied with 0.7. So that's going to be, I think, 0.020, I don't know, 5 meters per second squared or something like that. Okay. In any case, for our case, however, the actual gravity is towards the center. So that's the actual gravity. But the fictitious gravity is, fictitious gravity is in the radially outward direction. Why? Because this is our center of rotation, okay? It is different than the center of the Earth. For a person on the equator, the center of the Earth is basically also the center of their rotation. But for us, the center of rotation is somewhere on that axis, okay? So as a result, because of that, fictitious gravity is not in the directly upward direction, it's making an angle. It's basically making an angle of 40 degrees. It's making an angle of 40 degrees with our vertical. Okay, so in any case, let me draw this thing again. Sorry about this. That's some kind of a geometry, right? So let's just draw it like that. So that's the equator. We are somewhere in here. Sorry, I'm going to do it again. Let me just draw some perfect circles in here, right? So let me draw the circle like that. And let me also draw a line like this. So that's for the equator, okay? And I think I don't need to do anything. All right. So what I do is, we are at this point in here, okay? So again, let's say that the gravity is along that direction. Okay, that's the direction. That's the real gravity. So that's the fictitious gravity, right? I'm exaggerating. Actually, this fictitious gravity is much smaller. So what I need to do is I need to add them up vectorially. So that means the total gravity is along that direction. So that's the total gravity as a vector, okay? Which means, well, that's the one that we are feeling actually, which means that if we just follow the downward direction in here, I mean, think of it like this. Suppose that you have some kind of a hanging mass in here, hanging object. So that hanging object actually points a direction. So if you just go down along that direction, you are essentially going down along this total gravity in here. And as a result, you'll basically end up not at the center of the Earth, but somewhere in here. Okay, that's basically what it means. So the direction which is directly down is not really pointing towards the center of the Earth. It's slightly deflected, right? But since I have exaggerated the magnitude of this thing, so there's some kind of an exaggerated distance in here. In reality, that deflection is not that much, right? It's basically an extremely small angular deflection. But the result of that is basically that, so in our location, if we have some kind of a bucket of water, for example, the surface level of that water is not going to be perpendicular to that vector, it will be perpendicular to the total gravity, which means essentially that the sea level in here, I think I'm going to use a different color. Yeah, blue color is nice for seas. Sea level will be something like that in here. Okay, because I know that the seas, for example, the surface will be more or less flat. It will be perpendicular to the total gravity. So it will be perpendicular to that vector. Okay. So that means that the shape of the Earth will not be a perfect sphere. It will be deflected from it. So as a result, that would be the correct shape of the Earth. Okay. Sorry about that. I mean, my shapes are not perfect, but that's basically the thing that I need to say here. So that's the correct shape, therefore, correct shape of Earth, right? Since the Earth is rotating, it's not a perfect sphere. It is something called a geoid. Geoid. All right? But if the Earth were not spinning around itself, in that case, the shape would be a perfect sphere. But since it is rotating, it is not a perfect sphere. Its shape is something like that, right? And the reason is that the total gravity, right, which means the real gravity plus the fictitious gravity, is not pointing towards the center of the Earth. And because of that, the shape of the Earth should be different. Don't we reach the center if we dig till the, don't we reach the center? Perhaps when you go down in here, so let me just show it like that, okay? Again, this is exaggerated. So when you dig down, so you're going to go down like this, but at this point, the gravity, direction of gravity will change. So probably you're going to dig it like that. So when you dig it, when you dig a hole, always digging in the vertical direction, probably you're going to be digging some curved path towards the center, right? I think you are going to pass towards the center, but the path that you would dig would be a curved path. Okay. In any case, so let me just add this as a note. So, I mean, there's some kind of an equatorial radius in here, and then there's some kind of a polar radius. You can read these values. So they are different from each other. So the difference between these equatorial radius and the polar radius, there is some kind of a difference. Just read this from somewhere. But just keep this in mind, since this shape is because of the result of the rotation of the Earth, the fractional change in the radius, right? That's basically the fractional difference in radius, difference in Earth's radius, must be of the same order of this fictitious gravity divided by the real gravity. Okay. I don't use any equations in here, I don't have any equation in mind. But what I know is that if the fictitious gravity is basically an effect of order of like 0.3%, then the change in the radius of the Earth should be an effect like of the same order of magnitude like this one, right? But it's not an exact thing. So as a result, this figure might be like twice that. That's also a possibility, or 3 times that, like a 1% change, or half of that. I cannot say anything about this, but this is some kind of an idea that can be applied usually. Again, this is one of the arguments that we can use without deriving any equations. So what we are saying in here is that if the fictitious gravity were 0, I know that these two radii would be equal to each other, would be exactly equal to each other. But because this is non-zero, they will be different. So as a result, I expect that this fractional difference in Earth's radius should be proportional to that quantity. And there should be some kind of a proportionality constant in between them. And since this is dimensionless and that's dimensionless, this constant would be some kind of a constant of like around 1, might be 2 or 3 or 1/2. I cannot say anything definitely without deriving this exactly. But this kind of gives me an order of magnitude of the size of this effect. Okay, so I will ask you to check this. But yes, that's actually indeed the case. You can be sure about this. That difference is about like, it's actually bigger than the height of the stratosphere. Like it would be like 50 kilometers or something like that. It is a very large difference actually. But in any case, so when you go to the poles, for example, you don't see any difference in the air pressure, right? If you go up to Everest, for example, the air pressure becomes extremely small. But in any case, if you go to the poles, you see that the air pressure is more or less the same. So as a result, the air also somehow follows the same kind of a distribution. All of this actually is because of the fact that the Earth is rotating. Is AE constant or changes by time? Well, it changes because we know that the Earth is slowing down. So you can actually also find that figure as well. I mean, so many seconds per century or something like that. There's a figure for that. For some reason, the Earth is slowing down because of its interaction with the moon. So as a result, it is slowing down, but that's something that can only be measured by very accurate measurements. So that's something that you don't notice. Okay. Any questions? We know that because of the global change in the climate, global warming. You know that there are these glaciers in land masses like, I don't know, Antarctica, for example, or the Alps and things like that. They are melting. And so as a result, the water is added up. So the sea levels will rise. Because of that, some properties of the Earth is going to change. Not in billion years, but in a few hundred years. I think all of the glaciers will melt. Not that much, right? I mean, even in like 30 and 50 years, people expect a significant change. So because of that, it is possible that the rotation of the Earth may also change as well. So I think they cannot I mean, the sea levels will rise, but there's some kind of an ambiguity in how to compute this, whatever. In any case, there are also other effects that kind of changes the shape of the Earth as well. I'll talk about this when we talk about the tidal waves. So, all right, so inside International Space Station, right? So International Space Station is some kind of a space station, right? So we know that this is in free fall, so that's ISS. And then there are these astronauts inside, right? But the astronauts inside are somehow floating, and they eat pizza and drink coffee, or I don't know, I mean, they do things like that. So in any case, what happens in here is that the acceleration of the ISS, right? ISS is in free fall. So as a result, the ISS has an acceleration which is equal to the local value of the gravity. Okay, so I mean the gravity at that location, whatever it is. So that's equal to G. Okay. In any case, so as a result, therefore, if I use the same kind of an argument in here, so let's say relative to ISS, then ISS, this is what I would say. So there is this real gravity, and there is fictitious gravity, right? But the fictitious gravity is the negative of the acceleration of the ISS, which means it's equal to minus the gravity. So therefore, the total gravity inside ISS is the real one plus the fictitious one. which is therefore equal to 0. All right. This explains why there is weightlessness in there. So actually, the gravity is extremely strong inside this space station. There is gravity there. But since this is an accelerated frame, and the astronauts somehow are using this frame as their reference, they have to do this somehow to correctly investigate the motion of everything. So as a result, when they add this fictitious acceleration, fictitious gravity, they find the total gravity inside to be 0, right? This total gravity is the real gravity plus the fictitious one. So as a result, when they throw a projectile in here, I mean, when they investigate the projectile motion, they throw a projectile, and this projectile basically is in free fall, but the free fall acceleration is 0, so therefore they see it as following a straight line. Okay. So in any case, I made a mistake in here, actually. This is not really 0, right? The mistake is this. The problem is this, actually. The problem is that the gravity actually is not constant. It changes everywhere. So its value is different at different points. So we know that the Earth is round, so there is a center of the Earth. So the gravity is pointing more or less towards the center of the Earth. So as a result, the gravity at that location, for example, is different than the gravity in here. It's a very small change, but they are different from each other, right? Also, the gravity at that location is actually much larger, much stronger than the gravity in here. And the gravity at that location is much weaker than the gravity in here. Sorry about this, I'm exaggerating, okay? Actually, there's not much difference between them. So as a result, when we compute the acceleration of the ISS, I need to take into account all of these gravities in here. This is a very difficult calculation, but usually what people do is like the acceleration is more or less equal to the gravity, like more or less at the center of this one. So I'm going to call this as G0, okay? So that's more or less exact. So the acceleration of the ISS, since ISS is like a large object, is equal to one of these gravities, but which one? Basically, the gravity at somewhere at the center of the ISS, right? So that's the gravity somewhere at the, sorry, around the center, right? Around the center. Around the center of ISS. Gravity somewhere around the center of ISS. That's true. Okay, I mean, it's just a value, whatever it is. So as a result, when I do this calculation, I have to add this. So the fictitious gravity is always minus G0. Okay. So that's minus G0 in here. But the real gravity might be different than this. Okay. So as a result, the total gravity is not equal to 0, but it is slightly different from 0. Right? So as a result, what they experience is something like this. It's more or less like that. So the total gravity in here is basically towards here, towards the center. And in here, it is also towards the center. Around the center, the total gravity is more or less equal to 0. In here, it is away from the center. And in here, it is away from the center. Okay, so there are these kind of structures in here, right? So it's very small, actually. So G tot has a magnitude about like 10 to the minus 6 meters per second squared. You can compute this easily. So 10 to the minus 6 meters is like 1 micrometers. And because of that, this is called microgravity. Okay. So the total gravity is actually non-zero. And since its order of magnitude is like micrometers per second squared, This is called as microgravity. So what happens is that if you just leave something in here, right? Let's say you just leave a pizza in here at rest, right? You just release it from here at rest. In that case, that pizza is going to move like that, more or less accelerate along these total gravity, and then end up somewhere in here. Okay, so a pizza also in here is going to move like that and end up somewhere in here. A pizza that starts from here probably is going to end up somewhere in here, and so on. Okay, so as a result, there will be some extremely small gravity in there, and I don't know how they can observe this, but I mean, it is observable. Like in 1 hour, perhaps they will see that the objects have displaced, right? But probably when you just look at them with your eyes, probably you won't notice these accelerations. Okay. Yeah, there's one more thing. Artificial gravity for spaceships. That will be used for interstellar travel, right? We are going to do this, right? We are going to go to the distant stars by the spaceships. So how do we produce? By spinning. Thank you very much. I mean, in any case, let me just say it like this. So if a rocket, for example, is accelerating, so let's say that it has an acceleration of the rocket in here. Okay, so in that case, that's basically relative to inertial frame, relative to an inertial frame. In that case, relative to the rocket, so that's relative to rocket. In that case, we will produce a gravity which is equal to minus the acceleration of the rocket. Okay. So as a result, I mean, if you somehow accelerate your rocket with an acceleration of 9.8 meters per second squared, then the astronauts inside will actually experience that gravity. And so as a result, they will basically be feeling nothing, feel the environment as if they are on Earth, right? So they won't be able to distinguish this gravity from the gravity they experience on Earth. But of course, if you want to accelerate a rocket, you have to spend some fuel, right? There's some kind of a fuel spend. And you don't want to do this because the fuel will be scarce. So as a result, what they want to do, I mean, that's the best idea, basically. So they will be moving with constant velocity. But in any case, I think that's the idea in here. So there will be some living quarters in here and some kind of another mass in here. So probably this one will be bigger. So they will be rotating around each other. Or which one is bigger? So this one will be bigger. I don't know. There will be some kind of a center of mass in here. So in that case, without spending any more fuel, they can produce a situation where there is an acceleration. So since they have a centrifugal acceleration, the astronauts inside are going to feel some kind of an artificial gravity. So that's basically the fictitious gravity. That's the centrifugal gravity, basically, when they do this. So there are many movies, actually, that makes use of this. I think the first one is like 2001, A Space Odyssey. I don't know how to write this thing down, right? This is like 1968 or something like that. It's Kubrick. And the novel is Arthur C. Clarke has written the novel. But in any case, somehow Kubrick was able to actually do this. Somehow he was able to take a shot of the inside. So in that case, it's just a circular or a torus-shaped spaceship. So they basically walk inside spaceship. So they just go around, and somehow he actually was able to take a nice shot of this thing. So you can actually see that the astronaut is actually moving around. I don't know how he did it. Like, this is like in 60s. So I don't know. I mean, you may want to actually look at this. Probably in YouTube, you can actually see some parts of that movie that actually shows you this part of the thing. But of course, I mean, there are some modern versions, modern movies that also does these kind of things as well. Okay, so let me stop here. Next week, we will be starting with a new chapter.